I'm going to just jump right into the topic. Again, if you can't hear me, let me know at the back. So today's lecture is going to deal with what neural networks are. In the introductory lecture, we had an idea of, well, let me correct myself. In the introductory lecture, we went through some quick discussion of what is a neural network at a very, very high level. But then what can these things actually represent? So let's go through a quick recap of what we covered in the last class. First, we observed that neural networks have become the state of the art in many AI-related tasks like speech recognition, machine translation, playing smart games, driving cars, sticking captions on pictures, even being creative. Now, the thing about all of these tasks is that for a very, very long time, these were thought to be strictly in the domain of human expertise. Machines were not supposed to be able to do this, right? And then neural networks came along, and they show us that they can not only do this, they can actually do it very well. So what are these neural networks? They are essentially functions. There's a box, something goes in, something comes out. Every one of these tasks that we saw is really just the machine that performs every one of the tasks that we saw is just a function. It takes some input. It could be sensory. It could be a voice signal. It produces a transcription. It could be an image. It produces a text caption. It could be a game state. It produces a next move, but it's a function. So what's in these functions? And as we saw in the last class, to motivate the design of these functions, we went back and consider that these tasks are fundamentally human, right? And in the case of the humans, again, these are just functions, but the machine mechanism that's performing these functions is the human brain. Our intelligence, our consciousness is powered by the brain. So when we begin building neural networks, the original intention was to somehow try to emulate the structure of the brain, because obviously the brain is able to do it. Now, if you look into the brain we saw in the last class, here's what the brain has. It has billions and billions of neurons, all of which are connected in one gigantic network. So did we cover how many neurons there are in the human brain in the last class?
Tens of billions.
There's of the order of, so can someone give me a precise number? Pardon me? 10 billion. Better than that? You're getting close, within an order of magnitude. The estimates are between 80 and 100 billion neurons in the head. So that little thing on top of your neck, it's carrying a lot of stuff. Now, each of those neurons has the structure. You have all of these structures at the end, the dendrites, through which they get signals from other neurons. If the total signal exceeds the threshold, this neuron fires that signal and down the axon out to other neurons, where it feeds other. So our computational model too is going to sort of emulate the structure. The basic unit is something that emulates the brain. It's what we call the perceptron. And starting with this basic unit, we again emulate the structure in the brain where a lot of these neurons are interconnected, and we connect these up into networks of these computational equivalents of neurons, of these perceptrons. So let's look at each of these quickly. Again, we've done this in the last class. This is just for a quick recap. So each of these guys was performing something very similar to what the neuron in the brain performed. It gets a collection of inputs. It computes a weighted combination of all of these inputs. And if the weighted combination exceeds a threshold, it fires a 1. Otherwise, it does not fire. So the output remains 0. So if I write it out in arithmetic, here's what it's going to look like. The weighted sum of the inputs is computed out here. If that exceeds a threshold, this is going to fire. The output is 1. Otherwise, it's a 0. That's, again, very analogous to how the neurons in the brain were originally conceptualized as. These are actually what electrical engineers will call threshold gates. We'll get back to that. So I'm going to redraw this figure just slightly for mathematical convenience, but this is going to be important. Instead of saying that the weighted sum of the inputs must exceed a threshold, I can say that the weighted sum of the inputs minus the threshold must be greater than 0. It's exactly the same operation. So now I can define this variable z. Z is the affine combination of the inputs. So what's the difference between being affine and being linear? Anyone? Yes?
A linear combination has 0, 0 as a solution generally, and an affine combination passes through the origin.
Anybody? Yes?
The hyperplane that represents this doesn't pass through the origin?
So from this, that's correct. Both of you are right. From this perspective, if I got rid of this t, it's going to be a linear combination. If I have the t, it's affine. There's a formal mathematical definition of linearity. Anybody remember that? Yeah. Yes.
Superposition, that's additivity and
so if I take a linear function, if I have f of x1 plus f of x2, that's going to be f of x1 plus x2 for linearity. That doesn't hold for affine functions. So this is not a linear function. This is an affine function. You must remember this, because if you think of this as linear in some situations, this is going to come back and bite. But anyway, we compute an affine combination of the inputs. If that exceeds a threshold, if that's greater than 0, the neuron fires. So it's the equivalent of saying that I have a function f which operates on this affine combination of inputs and produces an output. And that function f is the simple threshold function. When the input is greater than 0, it outputs a 1. If it's less than 0, it outputs a 0. But then once you think of it this way, you can make some other modifications. We can replace this strong threshold function with something that's softer, right? So instead of having something like this, I can make it like so. And it's only a minor modification. It's still performing effectively the same operation. But once you relax this condition and say I can put something that curves, I can begin introducing other kinds of functions in this box, like these guys. So this one is a sigmoid. The tan h is just a shifted sigmoid. You have these other guys. This one here is a hinge function, often called a rectified linear unit. You have the softer version, the blue curve, which is called the soft plus. But all of these are different functions that could operate upon the affine combination of inputs to produce the output. So now, for this lecture, I'm going to continue assuming threshold activations. This function here is what we will call an activation function. An activation function is what operates on the weighted combination of inputs to produce an output. We're going to continue to assume threshold activations. But then that was just the basic unit. The brain itself is a large connection of these guys. So we're going to try to emulate that. We're going to take lots and lots of these units, and we're going to connect them up into one gigantic network. Typically, these networks, for computational convenience, we like to make them layered, meaning you have one layer of units, and one layer connects to the next layer. So if I call this layer 1, and this is layer 2 and layer 3, layer 1 doesn't directly connect to layer 3, it connects to layer 2. So these are typically layered structures. You won't always follow the structure, but this is the simplest structure that you can think of for computational purposes. Now, when you speak of neural networks, these days everybody's talking of deep neural networks. So what does it mean for this network to be deep? Depth has it's not just hand waving. Depth has a very nice formal definition. And we say, and depth is defined in the context of graphs in general. So anytime you have a graph of this kind, if you have a directed graph with a source and a sink, then the length of the longest path from source to sink is the depth of the graph. So over here, what would the depth of this graph be? Don't look at the text, just look at the figure. Right? So that's 2, because the longest path is this one, goes from here to here and back down here, right? This guy, although there's a path which is just length 1 from source to sink, the longest path is 1, 2, 3. So the depth of this network is 3. So you get the notion of depth. And when we speak of a deep neural network, we are speaking of layered structures. But even if it isn't layered, we are saying that the depth of the network is at least 3. It's got to be greater than 2, then you call it a deep network. This is just a formal definition of what a deep network is. So that's not very deep. 3 is not really very deep, but still, as far as definitions are concerned, that's deep. So here, for example, this is exactly, the depth is exactly 3, right? Now, yes?
Is the network acyclic?
Pardon me?
Is the network acyclic?
No, yeah, these are acyclic. We won't get into cyclical networks till halfway through the course. And we'll only spend very little time on cyclical networks, right? Now, so you have this network, but then the network is really performing functional operations. Just as we said, every single operation that we saw, whether it was, you folks at the back, do you mind shutting your laptops? Please shut your laptops. Yes. So we saw that in each of these functions, some input comes in and some out, and then you get some output. The inputs could be real or they could be Boolean stimuli. The outputs could be real or Boolean values. You can have multiple outputs from a single network. In fact, that was one of the novelties that Alex Bain introduced historically back in 1873, if you will remember from class 1. So given that it has this structure, and remember, each of these units is really, 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 really very, very simple. So given that you're taking all of these really simple units and composing them, what kinds of functions can these networks actually compute? What input-output relationships can this network model? And we saw in the last class that these networks can model any Boolean function. You remember that, right? We also saw that it can model any one-dimensional real-valued output. Now, what are the limitations? When I say any, do I really mean any? Is there any restriction on the network structure itself? So that's what we're going to cover for the rest of today's class. We're going to look at now this network structure that we just saw. It's many layers of perceptrons connected to each other, so we're going to call it a multi-layer perceptron. We're going to look at them. We're going to show how these are universal Boolean functions. We'll see that these are universal classifiers and that these are universal approximators, and we'll look at some of the limitations. So let's look at the MLPs as Boolean functions first. How well do multi-layer perceptrons model Boolean functions? You saw this in the last class. A single perceptron can perform all 3 basic Boolean operations, right? So how many didn't see that? Anyone who missed that bit? So just to be clear, in this figure, these are the inputs. X and Y are the inputs. 1 and 1 are the weights. And 2 is the threshold that you're applying. So if X times 1 plus Y times 1 is greater than or equal to 2, the output is 1. And then you can see over here that in this case, the output is only going to be 1 if both X and Y are 1. If either of them is 0, then the total combined input is less than 2. This unit is not going to produce a 1. So this is an AND gate. This is just a simple perceptron that's performing the operation of an AND. Here the weight is minus 1. So now if X is 1, 1 times minus 1 is minus 1. So that doesn't exceed the threshold 0, so the output is going to stay 0. On the other hand, if X is 0, 0 times minus 1 is 0, which matches the threshold. The output is going to become 1. So this is going to negate the input. This one here is an OR. The threshold is 1. If either X or Y are 1, then the total weighted input into this circle is going to be 1. So that matches the threshold. The output is going to be 1. So clearly, this perceptron can model any simple binary Boolean gate. In fact, it's much, much more powerful than that. So here, for example, it's a universal AND gate. I can say, for instance, that I want this perceptron to fire only if x1 through xl are all 1 and if the remaining inputs are all 0. If any one of these inputs is flipped, I do not want it to fire. That's a fairly complicated function, right? But you can see how I do this. The threshold is L. Now if all of these are 1, the total input they're going to produce is L. If any one of the remaining is also 1, that's going to subtract from the total. And so now the total input that comes in becomes less than L, it will not fire. The only condition under which this is going to fire is if the first L inputs are 1 and the subsequent L inputs are all 0. Right? So, yes?
What if, so the subsequent inputs cannot they take the value of 1?
Pardon me? So think of these. If any of these are 1, 1 times -1 becomes -1. So it's going to reduce the input, right? Similarly, I can have the universal OR gate. I want this perceptron to fire if any of these if any of these guys are 1 or any of these guys are 0. Now you can see how that is done, right? Let's consider the condition under which this should not fire. The only condition under which this should not fire is if all of these first L guys are 0 and the subsequent n minus L guys are 1, right? That's the only condition under which it should not fire, if it's an OR. And under that condition, these are 0, so they produce no input. These are 1, so the total input is going to be L minus n. I want the threshold to be just more than that. So the threshold is L minus n plus 1. This guarantees that this will fire under the condition that we've stated if any of the first L components are 1 or the subsequent n minus L components are 0, right? So it's pretty powerful. Here's something even more magical that it can do. It's a majority gate. So I can say fire, oh shoot, these should have all been 1. I'll fix this on the slides. Hira, can you take a note? This I have a mistake on the slides, right? So if assume that all of these weights are 1, then if I use a threshold of k, this is also wrong, right? Then if k of the inputs are 1, it's going to fire, correct? So this means that I can say fire if the majority of the inputs are on, or fire is some x% of the inputs are on. It's a very powerful function, and you can do it with 1 neuron, right? Still, we saw we can't do an XOR. And we'll see why you cannot do an XOR in a few minutes. But then, if you connect a bunch of these guys in a network, you can perform an XOR. And the way you would do it, this is X, this is Y. You have this one perceptron computing X or Y. This is computing not X or not Y. I AND the two. I'm going to get X, X or Y. So if I just take a bunch of these guys and connect them up in a network, I have 2 hidden neurons. We call them hidden because you're not going to see their outputs. The only output you're going to see is from the AND. So any intermediate outputs that you don't see are called hidden. And so those are hidden neurons. If you connect them up, you can perform the XOR. And so we saw that doing this, we can now begin building up more complex networks. You can get tedious functions like this guy, right? So MLPs can compute any Boolean function. They can emulate any individual gate. So these are what are called universal Boolean functions. We are calling them universal Boolean functions because if you give me an MLP, if you give me a Boolean function, I can always build an MLP that will compute it. It's a universal Boolean function. But then, here's the question. How many layers does this guy have? Anyone? It's got 3 layers, right? So how many layers will you need for an arbitrary Boolean function? Yes? Pardon me? 2?
You need to reduce the Boolean function to its simplest form, and then how many other terms you have, those many.
Yeah, so both of you are right? So you can do this with just one hidden layer. Why is that? A Boolean function is just a truth table, correct? I can write the set of all combinations of inputs on the left-hand side and their corresponding outputs on the right-hand side. I don't need to list all 2 raised to n combinations. I only need to list the combinations for which the output must be 1. So this is my entire truth table. For the remaining combinations, the output is 0. But this truth table can be expressed using a disjunctive normal form. So what this truth table is telling me is that the network must produce a 1 when x1 is 0, x2 is 0, x3 is 1, x4 is 1, and x5 is 0, which is the Boolean equivalent of saying not x1, not x2, x3, x4, and not x5, right? So I can have, for every row for which the output is 1, I can add one such clause. I OR the lot, the pluses represent OR, and this is a disjunctive normal form which computes this truth table. Now, given that I can do this, what would the MLP look like? I'm going to have one perceptron for each of the classes. And then eventually I'm going to have one perceptron doing the final OR, and voila. Using just one hidden layer, I can compute pretty much any Boolean function. So given this, why do you need depth? Well, the question is, okay, if I'm going to do this with just one hidden layer, how many neurons will that hidden layer require, right? So a one hidden layer MLP is a universal Boolean function. The problem really is the number of perceptrons that you will require in that single hidden layer if you have n input variables. So to understand how bad it can get, I'm going to use a different representation of the truth table. How many of you are familiar with Carnot maps? Right. Anybody who's an electrical engineer knows what a Carnot map is, right? And if you're a computer scientist, although this is a CS concept, you might not have encountered it, which is very paradoxical. But then this guy here, this box, is a box defined on 4 variables, W, X, Y, and Z. So there are 16 cells because four binary variables can combine in 16 different ways. So here, these are all combinations of Y, Z, 0, 0, 0, 1, 1, 1, 1, 0. These are all combinations of WX, 0, 0, 0, 1, 1, 1, 1, 0. So every cell over here is a unique combination of the inputs. And I've highlighted the cells for which the output is 1. So basically this is a truth table which has 7 rows for which the output is 1, and the remaining 9 rows have an output 0. Everybody clear? Now there's something very magical about how this box is designed. If you look at any 2 adjacent rows, or adjacent columns or adjacent rows, they differ in only 1 bit. The edges connect. So this is actually a cylinder, meaning this edge connects to this edge. This guy and this guy are neighbors. It also connects top to bottom. So this row and this row are also neighbors. So the whole thing is a toroid. And now let's look at this function, right? This function has 7 clauses for which the output is 1. So if I did a simple, very naive DNF formula, how many clauses would it have? 7, right? But then look at this. I can group these things up. If I group it, anytime you have boxes which are adjacent, you can group them up. And this group is telling me that it doesn't matter what W and X are. So long as Y and Z are 0, 0, the output is always 1, right? So in other words, this group is a single clause which is not Y, not Z. Similarly, this group tells me that, regardless of whether Z is 0 or Z is 1, so long as Y is 0 and WX are 0, 1, the output is 1. So this group is the clause not W, X, not Y. And this third one, I'm being suboptimal here. I can group these 2 guys here because they're neighbors. And that's going to give me a clause not X, Y, not Z. So long as you have adjacent guys, you can group these things up. And then you're going to end up with a DNF formula which is reduced. And so if I want to compose an MLP for this particular truth table, all I have to do is to express it as a reduced DNF formula. And the Boolean network for this function is going to need only as many neurons in the hidden layer as there are DNF clauses in the minimal DNF formula for the truth table. Now keep in mind that when I give you a truth table, finding the smallest DNF formula for the truth table is an NP problem. It's not really easy. But still, if it exists, it does exist, and the number of neurons you're going to require in the hidden layer is just the number of clauses, right? What is the worst case? Anybody? What is the worst case for a truth table of this kind? Pardon me?
There are no groupings.
2 to the power n.
So, almost, right? What arrangement of 1s and 0s simply cannot be reduced further? Yes? Yeah, thank you, right? There you go, right? Once I do this, there's no way I can group things. And if I cannot group it, how many neurons will I require in the one hidden layer? In this case, I'm going to require 8, correct? So suppose I have the three-dimensional, or this is actually, this is the three-dimensional equivalent of the Carnot map. It has 6 variables. It has 64 cells. And here every alternate cell is a 1. How many neurons will I require in the hidden layer? 32, right? So here you go. In general, if I have n inputs, in the worst case, I'm going to require 2 raised to n minus 1 perceptrons in the hidden layer. So although you can actually compose this whole function using just one hidden layer, that hidden layer is going to be exponentially large in the size of the input, right? What happens if I make it deep? Can you see how this would actually be reduced if I make it deep? Anybody? What is this function really?
We could have like a combination of 4 variables in one layer and add 2 more subsequently.
How? So I'll give you the hint, right? This is just W XOR X XOR Y XOR Z. XOR flips every alternate cell, right? This is U XOR V XOR W XOR X XOR Y XOR Z. And how many neurons did we need for an XOR? 3, right? I can do an XOR with 3. And I can do this with 3 neurons and 6 connections, or I can do this with 2 neurons and 5 connections. So you can actually go below 3, but I'll use the 3 example for now, right? So in that case, here's how I can do this. For every pair of neurons, every pair of inputs, I can compute an XOR. So first, W XOR X is going to be done by these 3 guys. Then that output is going to be XORed with Y, 3 more. So for every new bit that you add to the input, I'm going to require, here I have 4 bits, so I'm going to require 3 times 3 neurons. Here I have 6 bits, I'm going to require 3 times 5 neurons. So in other words, an XOR of n variables will only require 3 times n minus 1 perceptrons if I'm allowed to go deep, whereas if I'm fixing the depth to only 1, it's going to be exponentially large, right? So you see why. So single hidden layer will require 2 raised to n minus 1 plus 1. The final plus 1 is for the final OR neurons, whereas if you allow this to be deep, so this is going to be exponential in n, right? Whereas if you allow this to be deep, then you can do this in 3 times n minus 1. It's linear in n. The difference between linear and exponential is tremendous, right? So you can see why you need depth. But then it actually gets even better. The XOR is actually associative, correct? So if I'm doing an XOR, then I can, if I have something like this here, x1 XOR x2 XOR x3 XOR x4 XOR, and so on, I can group these 2 guys, and I can group these 2 guys in the same layer, and then I can perform the final XOR over these in the next layer, right? So if I do this pairwise, now observe something very interesting. First, I'm doing a pairwise XOR in the first layer, then I'm doing a pairwise XOR in the next layer, then I'm doing a pairwise XOR in the next layer, and so on. How many layers will I need for this network? Any?
The number of variables.
It's just log n, 2 log n, because you have 2 layers for each XOR, correct? So you're going to require only 2 log 2 n. See, I very helpfully put this on the slide. And here's what is really interesting. Suppose I say you're only allowed to use 15 layers. I give an upper bound on the number of layers that you're actually allowed to use in your network. I give you an upper bound on the depth of the network, regardless of the number of inputs. What happens? In the best case, you can go up to the depth. Beyond the depth, you still have an XOR. At that point, it's going to blow up, right? So what this means is that there is a minimum, for a given input size, there's a minimum depth of the network that is required to be able to compute universally any function. And actually, I'm kind of partially lying, but this is true for XORs. And reducing the number of layers below this minimum will result in an exponentially sized network to express the function fully. So you see why depth is needed, right? Also, there's also a minimum number of perceptrons overall that you will require. If you try to go below the minimum number of perceptrons for whatever depth, for whatever width that for whatever depth you choose, then you will not be able to compute the function. In fact, for an XOR, if you miss only one perceptron in the minimum architecture, what will the error be? 50%. You miss one neuron, you're going to be wrong half the time. That's how bad it is, right? So just to give you an idea of the criticality, think about this. An XOR, you take away one bit, you're screwed, right? So just the criticality of the structure and the depth of the structure sort of comes across. Now, I've been talking about neurons. You should really be talking about the number of connections, because the actual number of parameters is the number of connections. And in this example, there are 30. This is the number that really matters in software or hardware implementations. And networks that require an exponential number of neurons can require a super exponential number of connections, because you have an exponential times an exponential, right, in the worst case. So deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if recast using one layer, only one layer, even a fixed number of layers. And it gets worse. Suppose I have a function which is very complicated, but if you break it down, it's a lot of funky computation, and then at the end you get a bunch of outputs which must be XORed. So at this point, if you limit the number of layers you can have beyond this, again the network is going to blow up, right? So just as a note, I've been talking about the XOR. The XOR is a very special function that people who work on these problems like to work with. It's a parity problem. You're computing the parity of your input sequence. And the real statement is that any Boolean circuit of depth d, a fixed depth d, using AND, OR, and NOT gates with an unbounded fan-in, which means any single gate can take any number of inputs, must have a size 2 raised to n raised to 1 over d, right? That is the theorem. Alternatively stated, there's an arithmetic class of circuits called AC. AC0 is the set of circuits which are polynomial in size and fixed depth. You cannot compute the parity problem universally with a fixed depth network. If you limit the number of neurons in your network and you limit the depth, then you cannot compute parity, which means that at least on the parity problem, there's a law for the majority of problems, you're going to be wrong 50% of the time, which means you might as well just save yourself the computation and flip a coin, right? Now, this sort of comes across very nicely in the XOR, but to be clear, I'm just using although it looks complex, I'm using a very trivial example. The real statement, this is Shannon's theorem, it's very nice. It says that for n greater than 2, there is a Boolean function of n variables that requires at least 2 raised to n over n gates, regardless of the depth. What this really means is that for any reasonably sized n, say 10 dimensions, 20 dimensions, 30 dimensions, the majority of the functions will require an exponential sized network, which means that if you took 20 variables and you threw all 20 all possible functions of these 20 variables into a pot and randomly pulled out one of these functions, that function is going to require an exponentially sized network. And in fact, he showed that if all Boolean functions over n inputs could be computed using a circuit that's polynomial in n, then p equals np. So everything, if someday someone just comes along and shows that p equals np, then I have to discard this lecture. Now, so here's a summary. An MLP is a universal Boolean function. It can represent a given function only if it's sufficiently wide, it's sufficiently deep. You can trade off depth for exponential growth of the size of the network. And the optimal depth and width depend on the number of variables and the complexity of the Boolean function, where by complexity I'm speaking of the minimum number of terms or the number of terms in the minimal DNF formula for the function.